Hi, in this video and in a few other videos that I'm going to make in the next days, I'm going to talk about some topics of plasma physics which I've been studying for some time now. And these are particularly interesting topics which deal with the modes, modes of oscillation or perturbations which are driven in the plasma, particularly in magnetized plasmas, under particular circumstances, under particular conditions which are relevant for fusion plasma, so per nuclear fusion by magnetic confinement. And the subjects have been described and explained very well in this document, which is a sort of thesis by Bruce Scott named Low Frequency Fluid Drift Turbulence in Magnetized Plasmas. And for those of you who have not seen my previous videos, I've been studying this document for a while. Now I'm trying to study it in depth to try to get as much as I can from this, because it's very well written. It's full of things which are very interesting and also useful for my purposes. So the kind of dynamics which I'm going to talk about deal with the fluid motions. So they are kind of motions which are studied here in the fluid framework, so with fluid equations, and involve magnetic field, so magnetic perturbation, electrostatic perturbation, sound waves, and also drift motions. And they involve also so-called drift waves, which are kind of waves which are driven by these drift motions. And finally, they all come together in the theory of turbulence. So the last part will be dedicated to the study of turbulence, or at least some introduction to the main concepts of turbulence. And so I will try to split this whole subject in three parts. So the first part will deal with what is called the parallel dynamics. So it is a dynamics which is somehow simplified. It is in a homogeneous framework background. So basically without equilibrium gradients, which can cause advection, so say drag of the quantities by some fluid motion, by equilibrium motions. And it takes place mainly in the parallel plane, although it depends also on the wavelengths or let's say characteristic length in the perpendicular plane. The second part will deal with the perpendicular motion. So here the advection by the drift velocities caused by the equilibrium gradients will be included, and so the dynamic will be more complicated, but it will be still linear. So I will still deal with the linear modes. And finally, I will consider also the nonlinear effects caused by the advection by the perturbation fields on the perturbation themselves. So there will be quadratic nonlinearities. And all of these will have the purposes somehow of giving a general overview of the subject of these very complicated dynamics which take place in the plasmas, and how the different modes interact with one another, and how they all contribute to generating the turbulence, which is a very important subject in plasma physics, in particular for fusion application. So I prepared some slides, and now I will give you some equations. To begin with, I will remind some concepts, or better, I will define some conditions, some hypotheses, which are necessary to proceed in the calculations. These are necessary because this is somehow a simplified approach to the problem. In principle, the things can be much more complicated than that, but even with this limited or somehow reduced, let's say, model, more simplified, things can be already quite complicated. So the thing we are dealing with is a plasma. So I don't have to remind you what is a plasma. If you want, you can take a look at my videos in Italian about nuclear fusion by magnetic confinement, and there I will describe everything from the beginning. Anyway, the plasma is made of electrons, of course, and then I'm considering only one single species of ions. In principle, there can be many species of ions, but this would complicate the picture very much. So I prefer to consider one single species of ion, and it is all immersed in a uniform magnetic field. This is important because in nuclear fusion by magnetic confinement, we always have one equilibrium intense magnetic field which introduces some dynamics such as the gyromotion of particles, the Alfvén waves, and so on. In this quite limited, somehow simplified approach, still we have many phenomena which take place in the plasma. For example, we have Alfvén waves. These are magnetic field perturbations, where basically the plasma and the magnetic field oscillate with the same frequency, and they basically interact with one another. And they are, in this case, I consider transverse Alfvén perturbations. So they are Alfvén waves which oscillate in the plane perpendicular to the magnetic field and propagate parallel to the equilibrium magnetic field. Then we have sound waves, which are compressive waves. They are basically periodic compressions and expansion of the density. So they are density perturbations. And then we have electrostatic waves, which are basically plasma oscillations. They are peculiar oscillations which are typical of plasmas. Plasmas are quasi-neutral, which means that the density, the ion and electron densities are equal, so that the plasma is globally neutral. However, we do not exclude that locally there can be some charge displacement inequalities, let's say, which locally create some electric field. And the plasma tends to restore the neutrality by driving these oscillations. And then we have drift motions, and these are typically slow motions, are slow dynamics, which take place in the plane perpendicular to the equilibrium magnetic field, and they are caused by these cross products between the magnetic field and other gradients. For example, you have electric field, which is basically the gradient of the electrostatic potential or the pressure. This is the Eckersby drift, which is very important, and we will see it even later. And this is the diamagnetic drift, and it is also important in some limits, in some cases. Here we also consider the possibility that Alfvén waves are coupled to the electron pressure perturbations. This is not part of the MHD or magnetic hydrodynamics framework, which exclude the effects of kinetic effects such as the electron pressure. In this case, this can also be included, and when this happens, we talk about kinetic shear Alfvén waves, or just kinetic Alfvén waves, because the shear is intended, is assumed. This is the kind of dynamics which is important. It is also complicated, and it will be explained better later. But before I move to the equations, I want to give you a picture of how this perturbation can look like. Here I've taken these pictures, these representations from the same document. I just copied them so you can see they are kind of vintage picture because they are hand drawn on paper. So this first picture represents the shear Alfvén waves. These are only magnetic perturbation. They exist in the single fluid model, so with just one fluid. And they couple basically the dynamic of magnetic field and fluid. These straight dashed lines are the equilibrium magnetic field, which are some parallel field lines. These wave-like shapes, so these continuous lines, are the perturbation, which are so transverse because the magnetic field lines bend in the perpendicular direction with respect to the magnetic field, and they propagate in the parallel direction. Here the v velocity is the fluid velocity, which is in phase with the magnetic field, and here the magnetic field lines are indicated by b0 plus b tilde, which means the perturbation. And so this is the basic, let's say, phenomenon of shear Alfvén waves, which exist also under the simple MHD model. If we want to see something a little more complicated, we can see this other situation. In this case, we are in this limit, which is I call the flux tube localization, because the dynamics takes place located close to some flux tube, which is defined by this. So we have again our equilibrium magnetic field indicated by the dashed lines. This time let's say the amplitude of the radial extent of the perturbation is very small, and in general it is comparable, or let's say in the same order of the ion Larmor radius. So the perpendicular length scales are very small with compare with the parallel with the length scale. And so in this case, the dynamics is more complicated, and we will see later that the perpendicular wave numbers or wavelength play a role. So here the dynamic is involving also these vortex-like structures. So the flow this time is not just in the perpendicular direction with respect to the magnetic field, but it is rotating, let's say, somehow causing some vortices in the perpendicular plane. And these vortices has a phase which depends on the phase of the perturbation. So in this case, for example, velocity is rotating in one direction when we have maximum of the amplitude of the perturbation, and the opposite direction where the perturbation is at its minimum. This causes some complication in the dynamics. Here the V, so the velocity field is typically just the Icrosby drift velocity, but in general this can also involve, for example, the effect of parallel electron pressure, and this is what couples the Alfvén dynamics with the electron pressure dynamics. So this is a complication because it involves somehow a 2D dynamics in the perpendicular plane. In a more complicated manner, let's say, environment, we can have also drift motion, so the effect of advection by the equilibrium drift motion, so caused by the equilibrium gradients over the perturbations. This is not subject of these videos, but I prefer to show you already, and then I will remind it in the next video. So here we have this situation. This picture represents the flow patterns in the perpendicular plane, so in the perpendicular plane with respect to the magnetic field. Here the magnetic field is passing through vertically through this plane indicated by this cross. And as you see, the vortex flow is caused by the Icrosby drift, and it is rotating here clockwise. And we are also in the presence of some equilibrium pressure gradient indicated by grad P here, which is in this direction. So you see that depending on the phase of the rotation, the velocity can be in the same, in the opposite phase of the grad P, or in the same phase. And depending on this relative phase, this can increase or decrease the local pressure perturbation. So here we have some pressure perturbation which can be increased when the velocity is opposite to the grad P, or decreased if we are in the opposite direction. So in this case, the equilibrium drift motion can also trigger some perturbation, and this produces some more complicated dynamics, which will be subject mostly of the next videos. And then if we have also nonlinear, let's say, advection, so basically when this Icrosby drift is not just the effect of the equilibrium Icrosby velocity, but also caused by the perturbation, we can have quadratic nonlinearities. But this will be subject of the third videos. So now I will switch back to the slides. And let's see more in detail what happens. So a first effect which we must keep into account is the balance which takes place typically between the pressure and the electrostatic forces. This force tends to basically bring back the plasma to neutrality. So this is the so-called adiabatic response of the plasma, and it is typically taking place on fast time scales. Typically, this is a good hypothesis, a good, let's say, assumption for the electrons, which have a much smaller mass than the ions, and so they are more strongly affected by electrostatic fields. So whenever we use this assumption, we are in the adiabatic limit, and this is valid under some circumstances. When there is no balance between these two terms, so when this equality is not true, this drives some parallel current, which will have some consequences on the dynamics, and we also consider this. Then I have to, let's say, mention this fact that typically Alfvén dynamics, which causes the Alfvén waves, which I've already explained, is typical of the single fluid approach, which is the MHD or magnetohydrodynamics. And here the inertia, which is basically opposing to the force of the magnetic field, so the tension of the magnetic field, is provided by the ions. So typically the Alfvén dynamics is more related to the ions. Instead, the electrostatic oscillations, such as the plasma waves, are more typical of the electrons, but plasma waves are just the most simple ones. Actually, also the imbalance between pressure and electrostatic potential is an electrostatic effect, and it is in fact related to the electron dynamics. In fact, electrons respond to electric field much faster than the ions because they have much smaller mass. However, ions have much larger mass than the electrons, and so they provide the inertia. So sometimes the dynamics is driven by the electrons, but the inertia, which is necessary whenever we have some oscillation, is provided by the ions. So both the species of the plasma contribute to the oscillations. And so now that we have given some fundamental, let's say, elements to understand the dynamics, we can move to the initial system of equation, which we will consider, and then later I will simplify this system to deduce some results. So this is the four-field system of equation, which is a very successful model to describe the plasma dynamics, and many authors have used it to study different kind of dynamics, and I have used it too in some works. Basically, this is a system of four differential equations for four quantities. The variables are reported here, so are the electrostatic potential phi, the electron pressure, the parallel component of the vector potential A, and the parallel plasma velocity. The equations are in the order the vorticity equation. So this describes the evolution of vorticity, which is this nabla square, so square derivative basically of the electrostatic potential. Then we have the continuity equation or the pressure equation for the electron pressure. We have the parallel momentum equation for the ions, for the electrons, which is also called the generalized Ohm law, because this relates basically the current to the electric field, and it is also responsible for the Ohm dissipation. And finally, we have the parallel momentum equation for the ions. And the time derivative which enters here, so which is dE, with the E at the subscript, is the total derivative, which includes also the advective term. So this is called the advective derivative. So we have the partial time derivative plus the advection caused by the E cross B drift, which is the only one which is considered here. So in general, we have to consider also the effect of drifts in these equations, but we will see later that this can be neglected in cell limits and the equation gets much simplified. So as you may have seen, there is another quantity entering this equation, which is the parallel current, but actually this can be expressed in terms of the nabla square of the parallel component of the vector potential through the Ampere law. This is Ampere without the displacement current, which has been neglected. And so we have four variables for four equations. And then there are these two other parameters, which are defined here. Now, we have a system of four equations for four unknowns. And this basically means that the solution of the system leads to four modes of oscillation. So we have to find out four different modes of oscillation, which are eigenmodes or some equations. And we will see that this can be somehow splitted between some high frequency modes and low frequency modes. And this allows us to study the system of equation in two different limits, which are more simple. But before that, we make some simplifications. So the main one is that we neglect homogeneous, let's say we assume an homogeneous background. So we neglect the gradients of the equilibrium quantities, which means that the total derivative reduces to the partial time derivative, so without the advective term. And we also neglect dissipation, so we neglect in these equations the effect of viscosity, which enter here in the momentum equation, and the collision frequency, which will cause the Ohm dissipation. So the equations now are purely conservative, there are no dissipative terms. And then we can simplify them further by considering two different limits. The first limit considers high frequencies, particular frequencies which are much larger than the sound waves. So in the dynamics, in the equation, this kind of dynamics are allowed. And so if we make this assumption, we basically neglect the parallel velocity, which enters some equations. And so we have one variable less, and we can simplify them. And plus, we can put together the first and second equations, which involve the pressure, the electron pressure and the electrostatic potential. And so we can put two variables together, and we are left with this system of equations that you see involve this quantity, this difference between basically electron pressure and this combination of electrostatic potential times some other quantities. And this is an important quantity. We will see it also later. And on the other side, we have some other parallel quantities. And this can be further simplified by passing through Fourier transform. So we turn the gradients into wave vectors, k parallel and k perp. Here we have k perp square, for example. And then we can solve this algebraically, and then turn back into the real space. And so we bring back the gradients, and this becomes, it is a little complicated. I've just simplified. Anyway, it is not very difficult to do it. And so we are left with this wave equation. It is a wave equation because we have second order time derivative of this quantity, and on the right hand side we have second order gradient times some phase velocity indicated by VA, and this VA is written here in terms of this combination of quantities which involve the perpendicular wave vector k perp in this combination. And you see that this wave vector, this phase velocity depends on the perpendicular wave vector, which means that modes which have different perpendicular wave number or wave vector propagate with different velocity. So this is a dispersive wave. So imagine that we have some initial perturbation which have some spectrum in these modes, in these wave vectors. These modes will propagate with different velocity, and so they will lose coherence, will lose phasing, and so the wave will disperse in time. So this is a characteristic of these modes because we have introduced perpendicular dynamics, and so this introduces some dispersive effects. So this is the first result. The second result is obtained when taking the limit of low frequencies. In this case, this amounts to taking the adiabatic hypothesis. As I told you, the equilibration between pressure and the electrostatic potential typically takes place on fast time scales. So if we assume that we are in low frequency, this equilibration has taken place already, and so we are in the adiabatic hypothesis, which means that we are neglecting kinetic Raphène waves, and we also put the parallel current to zero, which is a consequence of the adiabatic hypothesis. And in this limit, we get this system of equations. So as you see here, we are no longer neglecting the parallel velocity, and our main variable will be the perturbed electron pressure. And again, we have to apply some manipulations. Again, we pass through the Fourier transform, we solve them algebraically, and then we put them together in a wave equation, which this time is expressed for this field, so the perturbed electron pressure, with this different phase velocity, which is now more simple, but again involves the perpendicular wave vector. So this is still a dispersive wave equation. So here again, the modes which have different perpendicular wave number or wave vector will propagate with different velocity. So I conclude by putting these results together, and so we have found that in these two limits, so the high frequency limit and the low frequency limit, we can find two different wave equations. First one involving this phase velocity, which has this complicated expression, and the other one involving this quantity. And the first wave equation evolves this field, which is the difference between electron pressure and electrostatic potential. The second one involves only the electrostatic potential. And as I said, the evolution of the system to the adiabatic configuration, to the adiabatic limit, typically takes place on fast time scales. And so the second wave equation assumes that this dynamics has already taken place. Again, okay, here I remind you that these phase velocities depend on perpendicular wave number. So if we have an initial structure, for example, assume some wave package which has some structure, so some shape in the perpendicular plane, which is following, for example, some initial density or electrostatic field distribution. Then with the passing of time, the different modes corresponding to this wave package will dephase, so we lose the phasing between them, and so the wave will disperse. So this is the cause of dispersion. And before concluding, I wish also mention that there is another solution that can be found, and for this I come back to the slide with the four-field system of equation. If we consider on the first two equations, you take the difference between the second and the first, and you neglect the parallel gradients, which can be reasonable if we are considering that the parallel gradients are much smaller, because maybe the parallel let's say characteristic lengths are much larger than the perpendicular ones. We are left with the partial derivative of this quantity, which is P normalized to the equilibrium pressure, minus rho square nabla perp square of this combination, which involves electrostatic potential, equal to 0, which means that this quantity is time independent, it is conserved, and this is called sometimes entropy. This is a characteristic or particularly important quantity which plays a role in the later stage when we deal with the turbulence. This entropy imposes some constraint in the evolution of the turbulence, concerning in particular the way in which the energy is transferred to the different length scales. So, for example, from large to small length scale, or vice versa. So this is one kind of constraint which follows from these equations, and we have consequences for the nonlinear evolution of the system. So this was just a simple introduction to the problem. In particular, here I just limited to the dynamics which takes place in the parallel plane. So as you see, those waves are propagating the parallel direction to respect to the magnetic field, but their phase velocity, which determines the velocity of propagation of the wavefront, depend on the perpendicular wave number, which means that the modes with different perpendicular wave number will travel with different velocity, and the wave or the wave package will lose coherence. So in the next video, I will talk about the perpendicular dynamics, which involve also equilibrium gradients, and so the advection by the Eckersby drift on the perturbed quantities. This will complicate the picture. And then in the final video, I will talk about also turbulence on the nonlinear dynamics. And altogether, this has the purpose of giving you some overview of this complicated dynamics which happens in the plasma. And so I hope that you enjoyed this, and see you in the next video.